Today our focus in geometry is going to be on dilations, and really dilations is another name for size change. So we're going to work on how do we set up a size change. So be able to go from something having an original shape to being twice as big or half the size. But the important thing with a dilation is that all the points have to be affected for the size change to be appropriate. So let's take a look at some examples here. First of all, when I talk about a dilation is a transformation that changes the size. All of the transformations we've looked at before, reflections, rotations, and translations, have all been ones where the size has stayed the same. This is not going to be true now. They are either going to be enlargements, where you're going to start with a shape and make it bigger, or they're going to be reductions, where you start with a bigger shape and then make it smaller. So if I were to do a size change, I'm going to set up rules just like I did before, but I wanted to give you an example of what one would look like. So if I were starting out with x, y, and I were going to double it, I'd have to double both x and y. I have to change them by the same number, the same multiple. So if it were tripled, it would be going from xy to being 3x and 3y. So that'll give you some idea of where we're going to go. So let's take a look at an example. First of all, it says that triangle PZG has the vertex of P being 2, 0, Z being -1, 1, and G being 1, -2. What are the new coordinates for a dilation with the centers 0, 0, and a scale factor of 3? So first of all, just so you know this, almost all the ones we're going to look at are going to be dilations with the center 0, 0, which means that we're not going to change it in any way as far as what the shape looks like except for its size. So let's actually take a look at a table here. I've kind of paused for a minute, made a table with our original points in our image. Now remember, whenever we've set these tables up first, it's important to do the table first and then graph. So we're going to do the same plan here. So on this one, if I want them to be a scale factor of 3, that means that for the image, I'm going to have to multiply both x and y by 3. So I am going to go through on all of these images, and I'm going to multiply the original point by 3. So if I multiply these both by 3, it's going to be 6, 0. If I multiply both of these by 3, it's going to be -3, 3. If I multiply both of these by 3, it's going to be 3 and -6. And now my job is to go through and graph both of these. So 2, 0 is P, and then I have -1, 1, which is Z, and then I have 1, -2, which is G. And I'm going to go ahead and connect my points. Now remember, if I'm doing a size change, I would anticipate that the triangle that's going to get made after this is going to be a bigger one. So let's go ahead and make the next one. So 6, 0, 1, 2. So 6, 0 would be here. That's P prime. Z is -3, 3. And then G is going to be 3 and -6. And here's G prime. And now I'm going to connect those. I make my line just a little bit smaller. I don't want to obliterate everything else up here. There we go. Let's try that. Now it does look like the other one is about 3 times bigger. That makes sense. I'm also going to go through, my image was this one that's in red. My original one's in black. Just so I have the color coding that makes sense later on. Okay, let's try another one. This one says circle A has a 3 centimeter diameter and a center C is the dilation of a concentric circle B with a 8 centimeter diameter. Describe the dilation. So first of all, before I even begin this problem, a couple words that I want to make sure we review so you're clear on them. First of all, diameter is mentioned here. And when I talk about a circle, the diameter is the length that goes through the center, and it goes from one side of the circle to the other. So that's one piece, because that's an important piece of vocabulary. The other one would be this concentric circle. A concentric circle are circles that share the same center. So if I was going to look at this, if I have a diameter of 3 centimeters, then if it was at 0, 0, I'd have to have 3 centimeters that went right through the middle. So if we went out 1.5 in each direction, that would give me a diameter of 3. Now, I'm going to do the best I can to make this circular-like. Kind of hard to draw in here and make it even, but I want us to have at least a sketch to look at. So this would be a diameter of 3 centimeters if we said each of these little units or blocks was a centimeter long. So half up here, so 1.5 and 1.5 would give me 3. Now this other one, this would be obviously circle A. To do circle B, it's 8 centimeters. So if I had my center at 0, 0, 1, 2, 3, 4, here's half of it. 1, 2, 3, 4, here's another half. 1, 2, 3, 4, here's another half. Here's another half. Now, with this circle, I'm going to do the same thing. I'm going to try to draw my pathetic looking circle. We'll pretend. Okay, let me fix this side that looks like it's got issues. That looks a little better. Okay, so if I was going to describe the dilation, there's kind of 2 ways to do it. If I want to talk about going from the big one, the big circle, to the little one, I can do that. To go from the big to the little would be a reduction. So if I were to put my fraction together, I'd want to put it together so that this fraction is less than 1. That's what a reduction is, a fraction less than 1, which means that I would have to take and go to 3 from the 8 that I have. So if I have a fraction, I want to be able to put those 2 measurements that I have here together in a way where it's less than 1. Now on the other hand, if I was going to go through and go from the little one to the big one, that means that would be an enlargement. So if it's an enlargement, I have to have a fraction that's greater than 1. So instead of putting the 3 on top here, I put it on the bottom and make the 8 go the other way. These are the ratios that allow that dilation to happen. So that gives us at least a point of reference. Okay, let's try one more. This one, big star on this. It's on the test and it's on the exam. The scale factor on the museum's floor is 1 to 200. So if you're thinking about a scale factor, 1 in the scale equals 200 in real life. Gives you an idea. The length and the width of the drawing are 8 and 6 inches. Find the actual dimension in feet and inches. So first of all, I'm going to have one here that's really built around length. Let me get rid of this. And I'm also going to have to do one that is based on width. So if I looked at these two, my length would be the 8 and my width would be the 6 inches. So if I'm looking at this, let's see, if I want to do my width or my length first, then I'll set this up and I will do 6 for my width. Now realize I put them up here because when we were talking about it, this is really scale to really real life. That's what that's going to give us. Also realize that when we do this, the answer that we're going to get is in inches. So we're going to somehow have to change that to feet when we get done. So first of all, if I was going to go through and solve this, our typical cross multiplying. So 1x equals 8 times 200. So 1x equals 1600, which is fine, but that's 1600 inches. So if I really want to figure out what this is, if I divided it by 12 inches, it would give me feet. So this gives me 133.3 feet. So as a fraction, it would be 133 1/3 feet. Okay, now let's take a look at this one with our cross multiplying. So 1x equals 6 times 200. So 1x equals 1200. And then if I were to divide this by 12 so I can go from inches to feet, then I would get that it's 100 feet. So they ask us to do dimensions. So that means like length by width. So my length is 133 1/3 feet. Or you could do 133 1/3. Either one of those is okay. By 100 feet. And this part right here is what they're looking for, the actual dimensions.